Okay, we should be live. Hey everyone, Fraser here. Welcome to this week's Open Space. This week I'm joined by Paul Geithner from NASA to talk about James Webb Space Telescope. You have been hammering me with questions about James Webb. We went and made an episode all about James Webb, which is done, and we tried to put it live earlier today, and it kind of it went a little over schedule, is all I'm saying. So but it should be live within a couple of hours after we do this live interview. So I had hoped that I would post the video, post a bunch of questions, post a bunch of interesting information that everybody would be able to digest that and have more questions. We messed up. I apologize in advance, but I still think this is going to be an incredibly productive conversation. So Paul, thanks for joining me.
Oh, you're welcome. Happy to be here.
So why don't you give people a bit of your background so they know who you are, what you do?
Sure. Well, I'm the Deputy Project Manager Technical for the James Webb Space Telescope project, which is run out of NASA's Goddard Space Flight Center.
Your cats.
In Greenbelt, Maryland. And so I'm part of the management team for the whole project. And there's three different deputies to the project manager, and I'm the one that focuses on technical issues and verification.
So specifically then, so you said, right, you're the deputy project manager. There's four of you, and then there's the project manager, I guess, of the whole project that you guys report to.
Right.
And so as the technical lead for this, what specifically are you working on?
Mainly resolution of technical issues, because there's always something that's coming up, even in this late stage of assembly and test. And I mean, I'm not the chief engineer. That's Mike Menzel. He's our mission systems engineer, but I'm the person in the management team that's focused on technical. And we have another one that's focused on financial, and another one who's sort of the overall deputy to the main project manager, who's Bill Oakes. And but yeah, so I think I have the best job, frankly, because I get to focus on just the machine and the ground system that's going to operate it, and getting it, working with the people that are actually finishing putting all that together, and making sure it's all going to work okay.
And so I guess if someone has a problem, what are the kinds of problems that they will bring to you?
Well, for example, I mean, the problems we've been having lately that have cost us some time have really had to do with just the complexity and the first-time nature of the Sunshield part of the observatory. The 5-layer tennis court-sized membranes that are actuated by telescoping booms and cables that provide the shade in the cold environment so that the telescope optics and the instruments can work. And it's just an incredibly complicated system, first of its kind, and there's always something going on. So it's not so much people come to me with problems, it's just the problems happen. And I work with the team of engineers that address them.
I'm working on another video as well, talking about this idea of doing in-space telescope assembly for maybe telescopes that'll come down the line. Yeah. And there was just some stunning numbers of things that need to happen when it gets deployed. And I forget the exact number. I can dig it up if I need, but there's some just 40 plus events that have to happen at once it just leaves the upper stage to deploy itself. There's more than 200 separate actuators, which are release mechanisms that need to. You can run through some of those numbers, because
sure. There's as far as devices, there's 178 individual non-explosive release devices that hold the whole observatory together for launch, because of course it's so large that it can't fit in the rocket in its deployed state, and the state it's going to be used to operate. So we had to fold it up very compactly so that it will not only fit in the nose cone of the rocket, but can be structurally very solid, so it can handle the rigors of launch. And so all these little devices, instead of explosive pyros that are sometimes used to separate things, these are all non-explosive, low shock devices, and there's 178 of them. 107 of those are associated with pinning the folded up membranes of the Sunshield together to be very compact, and all of them have to work. So as far as the number of things that happen, man, it depends on how you count, but there's a lot of things that happen. The deployments.
I've got it here. Actually, I've got my list here. Hold on. It's 20 different deployment events, 40 different structures, and 178 separate release mechanisms.
Right.
Yeah. And there's like some serious origami going on that. And so do you think that, and one of the things that I really kind of learned about this whole process is that it's like, if they had given you a bigger launch fairing, if they had given you a more powerful rocket, you could have, costs could have come down and timelines could have maybe have become shorter, because in fact it's getting materials that are that lightweight and yet be able to be strong enough to handle all the parts of the process. Like that, like you're at the maximum telescope that could possibly fit within a launch fairing of this size, right?
5-meter fairing. Yeah. I mean, your point's well taken. At some point though, you can't build a bigger rocket because that becomes impractical. And then we need to build it lightweight, yet strong to, even if it were large, to withstand launch. If we built a monolithic glass mirror, even if it's lightweighted quite a bit, like Hubble's main mirror was, making it 6.5, 8 or more meters, the problem grows geometrically with how the strength required for something that big, and then have it survive. And then just throw weight. The whole issue of, well, it's got to be, you need an awfully powerful rocket to get it to L2. It starts to become a runaway problem. So back to your point about eventually assembling telescopes in space. If we want to have greater and greater resolution and sensitivity, forecast weather on nearby exoplanets, right? Something really extreme. I mean, eventually you're going to have to. This is my opinion. You're going to have to assemble, send it up in pieces and assemble it in space. So, is Webb the last of its kind, where we build it all in one piece and test it all in one piece as best we can on the ground, fold it up, throw it into space and unfold it? Maybe, maybe not. Things like LUVOIR and other future large space telescopes are trying to, be an evolutionary step from Webb. Still the same idea, building it all in one piece. But yeah, if you want a hectare of primary mirror in space, you're just never going to be able to build a big enough rocket for that. You eventually, at some point, there's a breaking point. You've got to build things in space. We're not there yet, but it's in the future.
Well, and it's not like this hasn't been done before. I mean, look at the International Space Station. I mean, it is 30 plus launches all assembled by astronauts, and now robotic arms are doing things like soft capturing the Dragon capsules and birthing them. So there's, I think, as part of this presentation, and like I said, I don't want to give people too much of a preview, but it's sort of what's clearly in my head right now. A lot of the really interesting engineering challenges have been worked through, and so you can kind of see that it does feel like James Webb is sort of going to be the last of an era of the folded telescopes, and then the next generation are going to be these monsters, but they'll be like the Enterprise, constructed in space, flown in space, never had to land on Earth.
Right.
So let's give people then sort of a status report on where James Webb, as of November 2019, in theory, we are 14 months. So I'm sure to the minute, but we're about 14 months away from the actual launch date in March 2021.
Right. We are in final assembly and test. We actually just in September became one piece, became an observatory. So, it had always been multiple pieces and things being assembled. And the last several years, we were in two major halves. We were in the spacecraft bus and Sunshield half, and we were in the optics and instrument half, the telescope half, I'll call it, which is, you know, the payload, so to speak. And those two finally came together recently, and that was a big milestone for us, was getting those two together. And yeah, now that we're an observatory, we have one more set of environmental tests to go through, which actually aren't as rigorous as the ones that the two big pieces and other sub pieces went through already. Since all that stuff went through pretty good mechanical environments and went through thermal environments, this last set of environments is basically just mechanical, and just to make sure those final connections are sound and the workmanship of those is good. So we're, but we do go through one more set of acoustics and sine vibe tests, and one more deployment.
Of the Sunshield, or just the whole?
Of the Sunshield.
Yeah.
Partially of the optics. We won't be doing the secondary mirror support structure anymore, for example. We already had to run for record on that. But we are doing one more full deployment of the Sunshield. So, and it's one of three full flight deployments on the ground of the Sunshield. You know, the first one was before we put the Sunshield and bus through its own vibration and thermal vac environments. And the one we're just finishing now is the post set of those, post environmental set of those. And soon we'll be, we're making a few minor repairs and tweaks to the Sunshield itself right now, as we're about to fold it all up and then put it through environments one last time, and then unfold it one last time. And that last deployment, of course, has to go like it needs to go for everything to work in space. So, but yeah, that's what we've got left, is finish a few tweaks, fold it up, put it through environments, which will be similar to the levels that it'll see on flight, as opposed to a few dB higher than that. And then do an unfold, check it out, fold it up one more time, ship it to the launch site in South America, and then put it on the rocket and launch it.
Yeah. So, and right now, is it back at Goddard right now? Because I know it was on the West Coast. Is it back in?
It's still on the West Coast. So
okay.
The Northrop Grumman plant in Redondo Beach in the LA basin, that's where the bus and Sunshield were put together. So the telescope was assembled at Goddard and then sent to Texas for end-to-end optical testing. You know, I know we've talked about this before, but we took a giant vacuum chamber left over, a relic of the Apollo era, and we refurbished it and installed all kinds of sophisticated optical test equipment in it. And we put the telescope minus the Sunshield and the bus inside there. And we ran that chamber down to super cold temperatures. We got down as low as 11 Kelvin, because the telescope itself, when it's in the shade, the Sunshield will be run quite cold, anywhere from 20 something to 50 something Kelvin. And we needed to run light all the way through the system in the telescope in its deployed state, and verify that not only it worked, but we could phase the mirrors, because of course we're going to launch it and we'll have to line all the mirrors remotely. So we did all that testing, and then we sent that to California to meet up with the Sunshield and the bus assembly. And that was a little delayed from our plan several years ago, but we're on track now. But yeah, so everything's in California. It's all in one piece in a big clean room out in Redondo Beach, California.
And so then the next big step is it gets put into, you do these final set of tests, and then it gets put in the shipping container, and it's going to go directly from Redondo down to South America, or is it coming back home first?
Yes. We're going to go straight from there to South America. So we'll go by ship through the Panama Canal and right to the receiving dock that's on the Karoo River in French Guiana. That's the same place where a lot of other payloads and rocket bits come in to the spaceport there. And so we'll pull in there and we'll transfer to their facilities, and we'll do our final red tag, green tag, so to speak. So things that come off and things that have to go on. We fuel the spacecraft. We're fueled with hydrazine and nitrogen tetroxide, and that's for mid-course corrections on the way out to L2, and also for years of station keeping and momentum management and major pointings. So we need fuel, but that fuel is some nasty stuff. It's standard spacecraft fuel.
Super poison.
It's hypergolic and it's really horrible stuff, very hazardous. So one of the last things we do is, with the red tag, green tag, we fuel the spacecraft, and then we actually transfer onto the Ariane and a few last things before it's encapsulated in the fairing, and then it rolls out to the pad and it launches.
Yeah.
And that's like that's about a 3-month launch campaign to do all that.
Right. From like when you get it to South America, from when it actually takes off, you're looking at 3 months. Right. Yeah. Okay. All those activities. Are you going to be heading down to French Guiana to participate in that? Or are you going to be able to?
That's the plan. I'll be working with our lead, our integration and test lead, Mark Voighton, and just running the show down there with the Ariane Space and ESA and Kness folks.
Yeah.
And right now my place is in is down there for launch, and then immediately after come back and go to the Space Telescope Science Institute where the Mission Control Center is.
Yeah.
A lot happens in the first few days, first hours and days right after launch.
And from how long from when it launches will it take to actually then do its deployment? So how long is that journey out to L2?
So the journey out to L2 is about a month. I think it's the 29th day after launch that we actually nominally that we'll insert into this orbit about the L2 point. Most of the deployments will be done in the first roughly 2 to 3 weeks. The solar array is the first thing that comes out, and it's automatic, and that's minutes after we separate from the Ariane second stage. I think powered flight is about 26 minutes, and we'll separate, and then with somewhere, I forget the exact timeline, but it's only minutes after we separate from the second stage that the solar array comes out. We acquire the sun. We start making electricity so we can get off the battery, and then we start the major, the Sunshield deployments, the big pallets that kind of to which the membranes are all pinned and surrounding the optics in the launch configuration. Those fold down. It's about 2.5 days after launch. But in between there, we have a couple of very critical burns. One weird thing about Webb is we can't point the wrong end at the sun, right? We have to keep the optics not pointed at the sun. So we've asked the Ariane folks to give us an underburn, and we'll make up the last little bit of delta V to get to L2 with our onboard scat thrusters. If we got a too hot a burn from the Ariane, what a normal spacecraft would do is like turn around 180 degrees and then thrust towards the sun. Well, we don't want to thrust towards the sun. We can only thrust away from the sun. Right. So it's
like you can't for a moment let those optics look anywhere near the sun.
I mean, they're going to get a little bit of sun actually during the early phase of flight until we start deploying the Sunshield. But as long as it's not direct and for a long time, so we're going to be like in a barbecue roll, and we're going to be at shallow angles, and the sunlight may reflect off the mirrors, but the composite structure that hold them, the precision optical bench that holds all the mirrors together, if that gets too hot, it'll the glue that holds it all together will soften and it will all that align.
I did that to a telescope. I was using a telescope. I was observing a solar eclipse, but I was doing the projection method. Right. And so I had my telescope pointed through the window at the sun, and I was sort of being really careful about it. And I was projecting the sun, and I was watching the eclipse. And then I left my telescope for a whole day, and then it went through the whole day. And the next day, the sun came back through and burned out the optics and melted the glue, and because I'd left it, right? I'm like, oh, and now the sun's moved away, and so then we're done. And then it came back around the next day and melted the inside of my telescope, and it wasn't ever right again.
Ouch. Yeah, we're trying to avoid that.
Yeah, exactly. Yeah, you just do not want that. All right. As promised, though, I would love to get everyone's questions. I know that a lot of people have a lot of questions, and hopefully we can get through as many questions that both I have and the viewers have. So, Greg Guthman asks, why did you not use Florida for launching James Webb? Why is it going on an Ariane rocket?
Oh, that's a good question. So it's got an interesting story. So when we were first putting the program together in the mid-late 90s, we wanted international cooperation because you can get kind of more bang for everybody's dollar doing that. And our European partners, European Space Agency and the Canadian Space Agency, they're our partners on Webb. They wanted to partner with us on Webb like they have with Europeans in particular, like we're partners on Hubble. And on Hubble, and it'll be the same on Webb and a lot of other science missions, the scientists compete for time on observing time. And it's a merit-based peer review process to gain time. But the deal from the Hubble days, which goes back to the 80s, is that European scientists were guaranteed 15% of the observing time, whether they won less than 15% or more. At least they'd be guaranteed 15%. Turns out Europeans earn by merit something like 21% of the observing time on Hubble. So, but they wanted the same guarantee for Webb time. So we said, okay, that's great, but we need like 15% worth of value contribution. So it's in kind. And so 2 of the 4 instruments there's kind of 5 instruments, but it's 2 and 1 on the guider. But anyway, Canada provides a science instrument that's part of the guider instrument. And Europeans provide the workhorse spectrometer, the near spec, and the mid-infrared instrument. And that's great. That's a lot of value, but we're like, we need something else. They had offered, well, we've got this spacecraft bus we've developed for Herschel. Could use that. And we're like, yeah, but the interfaces are difficult, and it runs into difficulties with what kind of design information regulations that say what kind of design information you can share with foreign partners, even if they're your close allies. So that wasn't going to work because of the complexity and the number of interfaces with the spacecraft to everything else. And obviously optics is kind of a strategic thing, so we couldn't go there. So we said, how about a rocket? And at the time, this is about in the early 2000s, there wasn't a launch vehicle at that time that met the strict requirements for a flagship mission of Webb's class. You want a very reliable rocket with a long proven track record of success. And the Ariane 5 was the best thing at the time. And, that's a lot of value. So by throwing that into the mix, that gave, that's how we got to the roughly 15%.
Right.
And Europeans were gracious and agreed to include that in the package. And so that's how we ended up on an Ariane. And of course, Arianes are flown out of the Guyana Space Center down in French Guiana, northern coast of South America. And that's why we're launching from there as opposed to on some other rocket. And so it's been many years, right, since we made that deal, but we designed around the environment and the interfaces that the Ariane provides. Even though we're on a standard launch adapter ring size and things like that, you can't just say, oh, well, I'm going to change from, this rocket to that rocket at a late stage of development. So, we baked that into our program way back when as part of the European contribution. And that's why we're launching from South America, not Florida. It's part of the Europeans' contribution to the mission. So we don't pay for it. The Europeans pay for it. We can't, regulations, US law and such, that we can't pay the Europeans for stuff and they can't pay us for stuff in terms of the partnership. So that's valuable contribution from the Europeans.
So it's trading. You guys worked out. They offered to bring a rocket and a bunch of science instruments, and NASA and Canada, we chipped in, and the US.
Yeah, I mean, Canada, geez, the guider comes from Canada. It's the thing that points the telescope. That thing has to work, or we're not going to be pointing anything. Yeah. So it's great. It's a big international project, and it's all good. So that's how we ended up launching out of there instead of Florida.
A question from Corey S. Is there any way to stow anything on JWST after it's deployed if SpaceX Starship is able to go out and do repairs in the future or retrieve it? So this is, that's just a version, but the question that we get a lot is there any, the repairs and upgrades that were done to Hubble were so wonderful.
Yep.
I know there are no plans, but what capacity, what is possible? I'm sure somebody has done a back of the envelope idea for what it might take to be able to go out and not necessarily upgrade it, but at least give it more fuel to lengthen its mission.
Yes. So, it's a good question, because I've worked on, my first job in NASA was working on Hubble servicing. And so I appreciate what servicing is done for Hubble. My first job in NASA was working on the corrective optics for Hubble. So I've worked on CoStar, which corrected for the axial instruments, and I worked on NICMOS. Webb is hard to service, but we did think because it's a cryogenic spacecraft. Half of its faces the sun and is hot, but most of the mass of the observatory is running at 40 Kelvin. So servicing it in its operational condition is, it's rather impractical, but that doesn't mean servicing is completely impossible. So one thing we have done, and that you mentioned, is we didn't preclude the ability for somebody in the future to go, say, put more fuel on it. The one thing that will limit Webb's life guaranteed is fuel. The reason we need fuel is for station keeping and momentum management. And Hubble doesn't have fuel, but it's in low Earth orbit within the Earth's magnetic field, so it can react against the magnetic field of the Earth to do momentum dumps for its reaction wheels, which is how it points, like Webb. And it doesn't really have orbit maintenance. When we had the shuttle, we used to give it a reboost every time. But Hubble's in an orbit that's good for many years to come. So, but with Webb, we're way outside the Earth's magnetic field. We have to use something to react. So we use reaction jets. And of course, L2 is a metastable point. It's not a garbage collection point, so to speak, like L4 and L5.
Yeah.
So we need fuel to maintain our orbit and for momentum management. And so it's the one thing that could limit our life. So we've made sure that Webb is a cooperative target for someone in the future, maybe with a robotic spacecraft, to go out and acquire us and be able to put fuel through our fill and drain valves and put more fuel on it. But as far as changing out instruments or working on the cold side, that's just never been a practical consideration.
But there's two parts to it, right? There is as you say, there is the fuel for maintaining, for station keeping at the L2 point. And there's also the helium coolant that's being used to bring the telescope down to its operating temperature for the mid-infrared stuff.
Right, the mid-infrared detector has a but that's a closed cycle cryocooler. So it's like your refrigerator at home, only a lot more expensive and a
But
lot
it
fancier.
does have a limited lifespan, doesn't it? For the amount of
No,
time.
no, theoretically
Oh, really?
it's
Okay.
yeah, it's closed cycle. It's like the compressor that runs your freezer and refrigerator in your house, except we're using helium for working fluid as opposed to a like a fluorocarbon or something like
But there is like the refuel valve, and as you said, the intake and output are on the exterior of the spacecraft, and
that.
in theory, a very careful, very cold spacecraft could attempt to give it some more operating fuel. There's a place to clamp on
Yeah,
if it needs to.
yeah. We have a standard um, launch interface ring. They come in standard sizes. We're one of those standard sizes, so a robot could go out, clamp onto the ring, and then our drain and fill ports are those are known locations. And by the way, these are all on the bus, which is always in the sunshine.
Right.
So you're talking a warm bus, always in the sunshine. It's not we're placing targets on blankets that can be used so that something that would acquire Webb would know its orientation. So
Right.
yeah, we're making it a cooperative target, and we're providing all the information needed for somebody in the future to know how to basically unscrew the caps, put fuel in, and screw them back on. Yeah.
And it's not like that ring is weightless. I mean, you had to account for that weight as part of the, and putting that ring on the spacecraft is perhaps payload that might not have been something else. So it's, it's.
I mean, it's there anyway because we had that. That's how we attach to the launch. That's how we attach to the launch vehicle.
Oh, I see. So it is the thing that you would be using for the Arion for the upper stage anyway. So you
Right.
might as well, right. So that is
Right.
there, and
Interface so somebody else can use it.
right. Okay. Okay. Um, that was the question
Yeah,
here.
we thought about servicing a long time ago. Webb's mission and architecture makes it really difficult. But the one thing that the one thing that guarantees it will only last a finite amount of time is fuel. And so we've made sure it's a cooperative target. If somebody figures out a way to go out and stick more fuel on it, we didn't preclude that as
Right.
an option. Right.
Nathaniel Kinky asks, a part of James Webb have been stored for quite some time. What is the JWST doing to combat reliability problems caused by long storage? So,
Yes.
is that a problem?
The only, not really. The only thing that actually has been an issue has been the battery. So the battery that we have for flight eventually will get too old. So we've been working a spare just in case. But the one we have that we intend to fly is actually is good for our planned date and a good many months beyond. So I think we're okay. But yeah, it's not so much age as it's how many cycles you put things through while it's on the ground, either because of gravity or the moisture environment. So there are all these budgets for, well, how many times can we cycle a filter wheel on the ground or run the cryocooler compressor at it's in the condition things are in now. For example, there's things like that we don't want to fold and unfold the Sunshield too many times. But we need to unfold it and refold it enough times to know that it deploys. And that's just a wear issue. So
Right.
yeah, some of the instruments have been around waiting for 7 years. So just that thought makes you nervous, but actually there's really nothing. It's how many times you cycle things mechanically. That's the main concern. It's not just sitting around hasn't really been an issue.
I can imagine though, like as there are delays, and if you're a developer, you know, and you're working on some part of it, like the, as you say, like the cryo cooler, or there's some part of the machine that you're working on, your instinct is going to be, I'm just going to run another, I've got a little time on my hands, I'm going to run another test. I'm going to try and throw in some more features. I'm going to try to make this more reliable or more robust or whatever. But each time you're doing that, on the other hand, you are taking away from the total number of times that these things can be fired up and run
Yes.
and shut
And,
off
every
again.
time you touch the thing, it's a risk. So yeah, the thing was designed to be in space. It's destined to be in space. It wants to be in space. We need to get it, we need to get it into space, because that's where it's belong. That's where it was designed to live. So, yeah, I guess the only other thing about hanging around that other not moving things is, there are dry film lubes on some bits and pieces, and, those, you don't want to leave those sit in a given environment for very long. So yeah, there are certain issues to the age, but it's not as, it's manageable.
Right,
And
right.
we've budgeted everything. I mean, there's a budget for everything. So we know how long we've got and how many times we can run things before we're bad, and we're good. We got a lot of margin. So.
Glitch Walsh asks, what will be the first target for James Webb? Has anyone decided on what that first target is, or even for first light?
Well, yeah. I mean, that's not my department. It's reminding me of that old Tom Lehrer record. Boy, I'm really showing my age now. That's like, how they go up is, but how they come down is not my department, says Werner von Braun. Anyway, there's a funny old record, but yes, the short answer is yes. There is a team of scientists are figuring out right now what the early release observations are going to be, and certain programs are being selected. Exactly what it is, and then what will show up in the New York Times first, for example, or something like that, I can't say. But yeah, the first set of observations will basically be to showcase the observatory's capability and potential, and should be pretty mind-blowing, I imagine.
So would that be like something cosmological, like looking at the oldest possible galaxy, or would it be something more like, here's a planet orbiting another star, or
yes. so Webb's got a broad range of themes. It's got early universe, ancient galaxies, first galaxies kind of theme. It's got stellar evolution, galaxy evolution theme. It's got exoplanets and the conditions for life themes, and so all of those will be addressed in a suite of early releases, early set of observations. But me being project management team, but not one of the scientists,
right.
So there's not a lot of details I can remember, nor can I give anyway if I did know them. So, but yes, there's going to be a whole suite of early release observations that'll demonstrate the whole, across the themes that Webb is going to address scientifically and showcase its capabilities.
Yeah, I mean, as you said, like the capabilities are, like when we talk about those cool pictures coming from the Hubble Space Telescope, the ones where it saw a galaxy as it looked just 500 million years after the Big Bang, it was having to use a whole other galaxy cluster as a lens to be able to observe that more distant galaxy. James Webb will do this directly. But then James Webb is also going to be doing its version of the deep field, where it's going to be able to see stuff that's maybe only 250 million years after the Big Bang.
That's the idea. We're going to look farther and deeper, try to see the first galaxies. And I know that part of the early release stuff involves gravitational lensing, as you mentioned. That'll be part of the early, cosmic dawn stuff in the early releases. But yes, we'll be seeing, because we're infrared, we'll be able to see higher redshifts. Part of the primary reason Webb was even conceived at the year even before Hubble was launched was to be able to see the era of the first stars and galaxies. So
Yeah, I mean, I just like I imagine it like right now, the kinds of galaxies that astronomers are able to observe are the ones that happen to be perfectly aligned in this way, while James Webb will just let astronomers look at whatever they choose, which is just a dramatic difference to go, yeah, we want to explore the entire universe at that distance and that age.
yeah.
So in doing research for my video on this subject, there was a lot of the the science goals of James Webb came out of the decadal survey, the one of the decadal surveys. I don't know, the 1991,
2001, I guess.
the 2001, yeah.
2001,
And because of its budget and because of its timeline, it's almost like it's gobbled up another generation of decadal surveys. And so the astronomers put this kind of infrared astronomy as their primary objective. James Webb is there to answer those questions, but now the answers have come longer and later than I think they had been expecting. So what kind of, do you think that had they known, I mean, now the die's cast, they don't really have a choice. You have to, now we're just a year and a bit away and then their answers will come. So what, and so a lot of that is sad, a lot of downsides, but one really interesting upside that I've noticed is that the exoplanets, the number of exoplanets when James Webb first launched was a handful, or when it was first, should have launched, when it was first envisioned, and then it would have had that 10 years of survival, and then it would have been done. But now there's 4,000. By the time it gets there will be 5,000, 6,000. Way more interesting targets for James Webb to look at. So are there some examples like that maybe the science has progressed, the questions have gotten more interesting, that maybe in fact this is a boon and not necessarily a huge sad delay?
I think you touched on it with the whole exoplanet theme. I guess in '89, when the first conference was held, that said, hey, we need a large aperture infrared telescope to follow Hubble, even though Hubble was a year away from launch. I don't think there were any exoplanets.
Yeah, there weren't any. 93, 95
Correct.
Was the first.
Sometime in the mid 90s was the first one, right? And then and then we've had Kepler, and now TESS is operating. So we have all these targets identified, rich targets for Webb to follow up on. That was a whole area of science that, didn't exist when Webb was conceived. And then I guess another one is, I'm treading on thin ice here because I'm not a scientist. So I just,
Neither am I. So,
I didn't stay at a Holiday Inn Express last night. But anyway, dark energy was something that wasn't even found, right? I mean,
98.
98, right? You had Adam Rees on one team, and you had Saul Perlmutter and another team. You had these two teams, and they won Nobel Prizes for this, right? So discovering observationally that the rate of expansion of the universe is accelerating, so I imagine Webb will help shed light on what 96% of the universe is that we don't understand, right? Which is like 3/4 dark energy and almost 1/4 dark matter.
Yeah.
Right. And 4% is stuff we're made out of. So that will be, I don't think scientists appreciated that at the time because they just didn't know, right?
Yeah.
So I've always thought that the greatest discoveries that Webb will make will be answers to questions that no one has thought to ask, even now, after years have passed, and it was supposed to be launched many years ago, still isn't launched, but should be soon. And if anything, it's more of you would think it would be less of a relevant tool after the delay, but I think it's become more of a relevant tool because its capabilities are broad and are right in a sweet spot for addressing so many questions.
Yeah, and I think that's sort of what I was getting at, is that with Hubble, it was designed to be upgraded. It was designed to be maintained. It was designed to be refueled and have its gyros and reaction wheels swapped out for, and just, you know, and so there was no real end date to when the Hubble mission ends. You know, it goes for, you know, we're at 1990 till, you know, we're closing in on 30 years now, right?
Yeah.
And it'll be 30 years shortly when the CoStar, when the actual instrument was upgraded and it was actually able to see clearly for the first time. And astronomers have pushed the capability of Hubble beyond anything they had ever expected, and were able to make all these discoveries: the exoplanets, dark energy, and even helping to map out dark matter. But James Webb, with that 10-year lifespan, you get this one moment where you start the stopwatch and you go, okay, quick, you got 10 years to science as hard as you can, and then it's over. And so it's like, if you could choose that 10 years,
right,
would it have been 10 years ago? Would it 15 years ago? Would it be now? Would it be, because once
I
it's,
imagine the scientists would have said, gee, in 2010, we would have done the cycle 1s through 5, you know, it would have been different than what they are now, or what they'll be 2 years from now. Right. So, and of course the observations are solicited and chosen and like planned in 1-year cycles. So as the state of discovery progresses, and as we know what we don't know evolves, the scientists will be able to adjust. But yeah, there's a finite life, right? I mean, Hubble's original mission was, even with all the servicing and everything else, was planned for 10 years. And it's gotten these extensions because it's been such a powerful tool. It's had these senior reviews, and it's like, yeah, let's keep operating it. Let's keep giving budget to operating it. And like you said, it's going to be 30 years in space come next April. Webb, if we get a good burn from the Arian and we do our mid-course corrections at the right times in those first critical hours, and we get good performance, you know, we could have, you know, instead of say 10 years of fuel after commissioning, maybe we can get 14 or 17 years of fuel if we get a good burn from the rocket and we get good. But of course, we have to budget for worst cases. But yeah, if we're smart in those early days of the mission, and we get nominal things happening, we can get some extra years that way, and then hopefully all the other stuff lasts a long time. You know, I'd love it if this thing were like Curiosity, right? And it just, you know, 90-day mission and went for years. So
the Spirit and Opportunity.
Opportunity. Yeah, Curiosity's still working.
Yeah.
But yeah, Opportunity was Spirit and Opportunity were 90-day,
you
know, required missions. Like our mission is 5-year requirement after 6 months of commissioning, but we'll have fuel for longer. And, you know, if cosmic rays aren't too hard on us, and the other environment of L2 isn't too tough, and we're still working, we're still kicking, I imagine, and it's still a productive observatory, I imagine that Webb will fare well in senior reviews and will getting used. But yeah, as discoveries are made and priorities change, the scientists will be able to adapt with the selection of what observations they want to make.
And then when it does wrap up, like, I don't think for a while people won't have the stomach to, or the priority to, launch another sensitive infrared observatory that has the same kind of capability. Like James Webb is Spitzer plus, right?
Yeah, Spitzer's aperture was a fraction of just one of our 18 primary mirrors.
Yeah. And like, maybe James Webb is the next generation on Herschel, right? But what is the replacement infrared instrument that comes after James Webb? I would be amazed if someone has one on the books. I know there's like HabEx, and there's a couple of interesting ones for the next one, but I don't.
Origin Space Telescope.
The Origin Space Telescope.
LUVOIR.
And LUVOIR, yeah. But LUVOIR is
But
is
that's going to be through near IR, right?
right,
Right.
right. And so you're not going to get that mid IR observatory anytime soon. So that
Yeah.
window into the universe will then close down when James Webb does wrap up its mission. And hopefully there'll be some kind of overlap, but it's also entirely possible that there will be other priorities. People will be working on other things. And then suddenly there will be no ability to see in that wavelength anymore to that kind of distance.
Right.
So it is interesting to me that it feels like this sprint, like the moment that it opens up and begins to work, people are going to be getting as much science as possible. And then it's going to, and then it will be wrapped up.
Yep. Yeah. True.
So then assuming, once it's out the door and it launches, where will you be putting your attention next, do you figure? Is that like up to NASA, or do you have an
Oh,
idea of what you'll work on after this?
me personally,
Yeah.
I do not know.
Yeah.
I haven't thought that much about it. I've just been so focused on getting this marvelous machine built, and knowing it's going to work. And then the commissioning is going to be hairy. That the Mars guys like to talk about 7 minutes of terror,
Yeah.
and and there's nothing they can do because Mars is 20 or more light minutes away, and everything they're seeing coming back is, hey, it's already happened. You're just seeing what it's like when the signal finally comes back, and it's all pre-programmed. But our stuff is more like it's going to be a few weeks of high anxiety, and with people in the loop. We're going to be a few light seconds away, and we're going to be commanding most of these deployments. And sure, they're stored command sequences, but it's going to be very complicated. And if anything goes off nominal, we're going to have to be flexible. And so a lot of the time we're doing right now on the ops side are, rehearsals. We're doing a lot of rehearsals of different stages of the early part of the mission. And, to get the team, it's practice, right?
Yep.
Get the team learning how to work, learning how to handle contingencies, on all kinds of contingencies.
Yeah.
So it reminds me a little of the movie Apollo 13, where they were trying to, doing simulations, trying to figure out on the ground how they could do a return to Earth with the the fuel they had, with the amount of battery power they had, because their fuel cells were they lost most of the fuel cells, and they had very little power. It's like, how do we do this without burning the one circuit breaker we got left, and
Yeah.
be able to maneuver? And they were practicing all this stuff on the ground. And it reminds me of like the stuff we're doing now, where we've just had our third early commissioning exercise, which focuses on just the first 2.5 days of the mission. And things are really time critical then. And we're practicing stuff like that. We're having more this month, and we have many rehearsals going between now and the mission, so that when the mission finally shows up, hopefully it's just like falling off the log.
So let me adjust my.
We can just we know what to do.
So let me adjust my question then. Of the next batch of telescopes, the with LUVOIR, HabEx, Origins, and Lynx, which were the next 4 that were suggested by now, and obviously we don't know which ones are actually going to end up being built, but which of those have technical challenges that you are fascinated and would love to be a part of helping to solve?
Well, they all have pretty daunting, exciting challenges. I helped out a little bit on red teams for Origins and for LUVOIR, and the teams that worked on those, it was really impressive the work they did. But boy, that the challenges are daunting. And for somebody like me that's been involved in Webb for a long time, and I'm really buried in the actual hands-on hardware, get it finished and launched part, and everything I went through with the rest of the team on developing the technology and then actually making it real, and the real hardware that works, and not just in a lab, but is going to work in space. I really appreciate, I'm humbled by how hard this is. And so, you read some of these things and it's like, oh yeah, well, we'll just cool this thing down to 4 Kelvin, no big deal. It's like, no, that's actually really hard. Just
That
because we
last mile, yeah.
yeah, just because we developed coolers that worked for the MIRI instrument, that wasn't easy. And so I know these things aren't going to be so hard for these next generation of observatories, and they're going to be generational like Webb was. Size matters with telescopes, and you know, so building something big and then with new capabilities so that you can do new science, you're pushing the you're exploding the envelope.
Yeah.
and it's daunting. I mean, the engineering, we're really pushing we're advancing the state of the art in engineering in many fronts with these new observatories. So they will take a long time and a lot of work to manifest as real things that get launched into space. And I'm just, after my years on Webb, I'm humbled by what it takes to do that. So yeah, the challenges, the coronography that some of these observatories want to do to actually try to image exoplanets around nearby stars. I mean, the stability requirements. It's just, I can go on and on. There's so many technical challenges that, make some of what we've done on Webb look kind of tame at this point.
I mean, my background is in technology as well. And like my favorites are just those problems where you initially you just think it's impossible, and then your brain starts to think of a couple of ways that you might try to take a crack at it, and maybe if you were able to just, and then you're hooked, and then you're in, right? And then you can't let it go, and you obsess about it, and you sculpt your potatoes out of it, right? So I think that those are the kinds of technology challenges that I find really, really fascinating. I find, after a while, you just sort of keep mulling over in your head because you think there's a way to crack into that problem. It's just give it enough time and run through some things that aren't going to work.
Yes.
So, after you've gone through the ones that haven't worked. Well, Paul, we're reaching the end of our hour. I don't want to take any more of your time, but thank you so much for joining us today. If people want to keep track of the status moment by moment, what is the best place to stay on top of everything that's going on with James Webb?
Well, our website and social media. So we have a wonderful director of social media, and she takes care of our, we have Facebook, Twitter, and Instagram. And of course, there's the website, jwst.nasa.gov. And our public affairs people are great. They're putting out wonderful stories and features all the time. So yeah, check out our website, search on any of the social media outlets, and you'll can see pictures and read about what we're up to and keep tabs on us.
And that next step, what's the next thing that people should be hearing of the test?
Right.
The mechanical test?
Yeah, the next big thing is finishing folding this up, and next year is going to be the acoustic and the final acoustic and sign vibe test of the whole observatory. So that will be late spring next year. And yeah, that's the next big thing. And then the whole unfolding and tensioning of the membranes one last time on the ground. That'll be quite something. That'll be later in the late summer, early fall next year, and then it's folded up and get it to the launch site.
Ian Geithner says hello.
Yeah, who? Ian? That's my youngest son. Hi, Ian. Yeah, awesome. There's actually not that many things left to do when I list them, but they take a long time, and the devil is in the details.
Yeah,
so.
Absolutely. Well, Paul, good luck. We are wishing you all good luck. We cannot wait for all the success with this telescope. We're all counting on you, so we can't wait. All right.
It's going to be cool. It's going to be really neat.
Yeah,
Thank you.
Wait. All right. Thanks a lot.
All right. Take care.
All right. Let me